Okay.
That works.
Well, first of all, thank you for the invitation to come to talk during this LunchMAR. I'm very happy to see this network continue to grow and pursue where we started a couple of years ago, and that's awesome to be still part of it. So my presentation today is about the climate change and climate in California and the DWR technical analysis that we are doing. What is decision scaling? I'll spend quite some time to explain kind of a procedure that we really think that's innovative for planning purposes. And briefly talk about the Merced and Tuolumne watershed studies, a little bit more focus on the Tuolumne watershed study. So most of you know that we are living in a Mediterranean climate. We are living through extreme and variable precipitation with the atmospheric rivers being the deciding factors on a drought or a flood year, and is very variable in time and location. Just a map with like the different average annual precipitation, big changes throughout the states, and I think it's important to point out that not climate change is not going to affect all the states similarly. So what climate change affect? How climate change is going to affect what would be the effect of climate change in California? And there is some well understood information out there that people can rely on it. The first one is the increase in temperature. We know that the temperature is going to increase, but we're not certain about how much, like what is the range part of it. There is also like good information about the change in precipitation. It's not quite sure if we are going to have less or more precipitation on an annual, on a year-to-year basis. However, we know that extreme precipitation may be more intense and create much more rainfall and snowfall sometimes. In fact, there is some papers from Fisher who say that probably like precipitation with which are larger than 99th percentile probability, so very large atmospheric rivers, may increase by 7% of intensity by degree Celsius. So you can imagine that by 2.4 degrees Celsius is like 14 more precipitation for this extreme. And that the graphic on the right from Gershnoff will show the distribution of atmospheric rivers and how they may increase by the mid-century. Where like the most, the dark lines show like the increase in chance, increase in probability, increase in frequency of changes in these extremes. And finally, we have also the good information about sea level rise. We know that the median future condition is around like 0.9 feet at the Golden Gate Bridge, and there is some estimate we'll raise it to 2.7 feet by mid-century. So that's kind of like the information that we are pretty comfortable with. And so how does this information, impact the watershed in the Sierra Nevada and in California? Specifically to Sierra Nevada, we know that the increase in temperature is going to move the snowpack in a higher elevation, increasing, runoff during the season. That's really the graphic on the left. The San Joaquin Valley being the most impacted out of the mountains in the Central Valley. The graphic on the right show the shift in the distribution of flows throughout the Sierra Nevada. So the bubbles show like the quantity of runoff over on the monthly time scale, and the red bubbles show the change if we continue on a similar greenhouse gas emission path forward. So you can really see the shift to the left of the runoff from the Sierra Nevada. And I should have said that at the beginning, my presentation is not so much about the managed aquifer recharge, but I think, climate change, the effect of climate change will make LunchMAR like more, will provide more opportunity to apply LunchMAR throughout the state, especially when we think about like the increase in precipitation for these large events, but also like in Sierra Nevada, the runoff, when you see that everything is shifted by a couple of months, we'll need to capitalize on that in the future. So there is a multiple choice question here. Sorry. And Orit, you're going to share the screen, right? Yeah.
Yep. So the question, how much snow loss is projected across the Sierras via models by the end of this century? So we have people responding.
And hopefully nobody picked my slide.
So I'm going to give people just a few more seconds to respond. Okay. So I'm going to share it so you can speak a little bit to these answers. Where most people thought it was either up to 50 or up to 65%.
So the response was up to 65%. It's just a graphic to show like the April 1st snow water content in inches. And yeah, that's something was very worrisome, is that, you know, if we don't have a snowpack at the end of spring, you know, how reservoir operators and you know, people who apply the water in crops and urban area, how are they going to manage this water? And that's, you know, again, LunchMAR can be very useful because you're going to have this contingency plan for future conditions. So in the department, we have done like multiple climate change studies. These, you know, since 2006, it really started with like mostly our Stillwater project and understanding how climate change may affect our delivery capability. And then over the year, we started to like, you know, be more active on other aspects of climate change analysis, where there is a requirement for the states to use climate change analysis to take decision on our investment approach, but also our planning efforts. There's really two types of analysis who are complementary in my mind and should be really one sole way to do climate change analysis is like a top-down, downscaling analysis type of climate change analysis, and then there is a bottom-up decision scaling analysis. And you can see that like the majority of our effort are like downscaling analysis, and I'll talk about, you know, the difference between the two. But you know, there is a big push in the department to move toward decision scaling, at least for our planning efforts. So what is a top-down downscaling approach? We start with our general circulation models, who are like big climatic models who are doing a pretty good job of representing like the energy balance on atmospheres and how it relates to on the temperature and precipitation, you know, globally. We use this information, and there is like right now 64 representation of future conditions that we have data for, and we downscale this information to the ground. When we downscale it, we use methodology statistical analysis to really to make it, to try to represent as truthfully as possible to what will happen, you know, in my neighbor, in my property. And then from this downscaling information, we run them through a system model or operational planning model, and we have a conditional system performance projection. So we're able to say, you know, that's my system based on like this specific projection, that's how my system responds. The main benefits is that GCM are the best available information related to future conditions. There is no better information so far. The aspect of change at the level, local level, are not captured by GCM due to the resolution of regional factors, but it can be captured by downscaling. So we are able to like downscale the information to a local level. Every GCM has multiple variables, so we can look at the wind, the energy balance, the precipitation, and so on. So it's a big array of information will come from these general circulation models. And finally, like every downscale scenario integrates and capture multidimensional changes. So that's the way that people have been doing, you know, climate change analysis so far, and that's what people, you know, prefer in general. But there is some challenges about that. The main challenges are about the choices. each of these general circulation models can be related to an emission scenario. So right now, when we say greenhouse gas emission as business as usual, is a pretty high level of greenhouse gas emissions, which is going to intensify the change in temperature. But there's some projection, and if we are able to curve our greenhouse gas emission, that's going to result in a much different picture. There's also like the way we downscale the information to the ground, the model selection on ensembles. So we can, we have 64 GCM, which one do we select? That's, it's really a choice based on the project manager. And then all the bias correction that we're doing when we manipulate this data. The other thing is every 5 years, we have new data sets from the UN, the IPCC group who is working on developing these models. And we have multiple different ways to do the downscaling process. So the planners will always wonder if the result would be different if they were using different methods or model selections. So the other approach is to take a bottom-up decision scaling approach, where we start without the GCM. We just use the GCM to understand what is the bandwidth that we may expect to change. And so we develop a time series, a long time series. It can be a 100-year, 1,000 years of observed data. And we start to perturb it by 1 degree Celsius, 2 degrees Celsius, 4 degrees Celsius. And we run it through our system analysis. So that's without doing anything. We don't know necessarily anything about the general circulation models. We are more concerned about the change that we may experience. But this change can be modeled through our system analysis, and we can develop some system response map, which is going to tell us how vulnerable our system is to a future condition. The nice thing is you can overlay them with our general circulation model to understand the probability of future condition and start to do adaptive planning. So by this method, we are embracing uncertainty because if we just do downscaling, we can select. It's very time computed, and so we can only select maybe one scenario. So in this case, we can look at a broader range of future conditions, build uncertainty on our decision making. Decision maker become more informed about their system. And I think that's one of the key aspects of decision scaling is really trying to understand how our system responds to a future condition. Identifying thresholds, when you want to take action and how much risk you're willing to absorb. And finally, isolate system sensitivity from the project climate signals. The main challenges with this method is that the sample number of perturbation can be as large as general circulation models. So you can perturb the climate in many different ways. And so the idea is not to make it more complicated here. The climate change impact analysis is limited by a number of perturbed variables. We can perturb precipitation, temperature, sea level rise, annual precipitation, interannual precipitation. And that starts to be a lot of layers to perturb. An incremental perturbation may not result in a linear response. So it's not because you change your temperature by 1 degree Celsius, 2 degrees Celsius, 3 or 4, that your system is going to respond linearly. And so there is more complexity on that. And finally, the GCM or the perturbation are not necessarily consistent. I mean, however we perturb our historical time series may necessarily, coincide with the same level of perturbation or the same vision of the GCM, the general circulation models are providing us. So here's an example. That's the Stillwater project vulnerability assessment that the department published 2 years ago, I believe, where we did a vulnerability assessment of the Stillwater project to climate change. And that was one of our first major efforts using decision scaling. So each of these dots, so the x-axis represents the change in precipitation on an annual base, and the y-axis represents the change in temperature from 0 to 4 degrees Celsius. The 0 points represents our current condition estimates. So that's where we stand at right now. That's the observed data that we have. And we have 1,000 year, in this case, we're using 1,000 years of monthly data to do our analysis. And each of these dots represents another time series of 1,000 years that has been perturbed by a change in precipitation and in change in temperature. So what we can do once I have all these 1,000 years of data modeled through our system analysis, I can figure out, how my system responds to a change in precipitation and temperature. So this colorful graph shows the Stillwater Project average annual deliveries, where at 0, we have 2.71 million acre-foot of deliveries per year. The black line, if you follow the black line, is like a contour line in a topographic map. So the contour line, the black line, represents the same level of performance of a Stillwater project. So for example, if I had 4 degrees Celsius to my system and an increase of 20% of precipitation, I have the same level of performance than at 0. If I fall on the blue, I'm able to export or deliver more water. If I fall on the orange, I deliver less water. So for example, at minus 10% of precipitation and plus 2 degrees Celsius, we are decreasing our system deliveries to 1.9 million acre-foot of water. So now you can superpose our general circulation models. So each of these dots represents one representation of the future condition based on the IPCC guideline. So you can see that, they all say that the climate is going to be warmer, but the array of range, the range of increase in temperature is from 1 degree Celsius to like almost 4 degrees Celsius by 2050. And the range of annual precipitation has the same range between minus 15 to like plus 30%. So it's a big array. And if you take the binomial distribution, so the distribution of this point in this square, you can see like what is the probability that's, where we're going to land in the future. So we can animate this picture, and that was one of my colleagues, Andrew Schwartz, we did his work. I think it's talking to itself of, how broad the uncertainty is, but, there is definitely a regression of where we're heading. Warmer climate and more variable range of precipitation. So now you can superpose the blob, or this like binomial distribution, on the surface response of the Stillwater project, and have a better understanding of what will be the capability of the Stillwater project to deliver water in the future. Again, the centroid of the blob really fall on a reduction in the Stillwater project delivery capability. In fact, the table on the right show like the performance metrics, several performance metrics of the Stillwater project, and the probability that by mid-century, the performance will be less than the current performance. One of the big one is Orville carryover storage, with being reduced by 95%. There is a probability, a 95% probability that the performance of the Orville carrier storage will get reduced. In fact, we can even predict by using probability what is the risk associated with it. So that's, by using this information that we are able to take some better decision, I believe. Because now we can, introduce the idea of adaptation strategies. And here the concept is not to try to increase the delivery, our ability to increase the delivery of the Stillwater project, but to try to maintain it. And so each of these adaptation strategy who are in dotted line could provide a better or a similar delivery capability than what we have right now. And there is different projects. For example, one of them is the Delta Convents. That's the tunnels that we are talking about. But there may be some other adaptive strategies that we can explore. And the next concept is, because I know how much each of these adaptation strategy can provide me to maintain the system performance, I can start to decide when I want to implement them. So over time, when do I need to jump from one adaptation to another? and by which period of time. So you can add the economic value behind it if you wanted to. So I believe I'm going to let Orit ask a survey question at this point.
All right, so here is our next question asking about these surface response plot. We recognize that these could be complicated to read, and we want to get a sense from you of what you think in terms of the complexity of the representation, and then if you have any thoughts on improving this explanation, if you want to add your thoughts in the chat or email it to Romain. And right now it's quite split between it's fine as is and it's difficult. So
yeah.
I'm going to give more people an opportunity to respond to how how complex concepts can be presented in the way that are understandable. I think that's the key question.
Yeah, I think it'll take people at least 2 times to fully grasp this surface response. So yeah.
Okay, so let's see. I'm going to give people just a few more seconds to let us know. Is this complicated to grasp looking at it, or does this all make sense? It's just an opportunity to think about how to present information. And I'm going to end the poll. So hopefully all those who wanted to respond had a chance to do so. And it looks like few people are going to provide some more specific input. So right there, you can see it's close to split.
Yep.
So, all right. Well, thanks everyone for weighing in.
Thank you. So now I'm going to change gears and talk about the Merced and Tuolumne watershed studies. And I think that will help you to understand how to apply it better. In fact, I should ask the poll question twice to see if there is an improvement on people understanding. So the watershed-based vulnerability and adaptation planning is really like a 2-study. There is a Merced River Basin flood-mar reconnaissance study that DWR talked about, a couple months ago, and the Tuolumne River Watershed Vulnerability Assessment and Adaptive Planning studies. So both of the studies are using decision scaling in 2 phases. The first one is to understand the vulnerability and try to do a vulnerability assessment of the watershed, and then look into the adaptive planning, evaluate the effectiveness of adaptation strategies. In the Merced is really focused on like the flood-mar aspect, adaptation strategy. In the Tuolumne, we want to look at the broader aspect in the adaptations. How we are doing it in the Merced, we're using paleoclimatic reconstruction of historical hydrology. So it's tree ring information that we perturb and run it through the system, and we stress test the watershed using decision scaling. In the Tuolumne, we're using an innovative stochastic weather generator. And like I mentioned, the goal of the Merced study is to really provide a proof of concept study to apply flood-mar and how we could implement it. The Tuolumne is more a R&D to improve our understanding of the effect of atmospheric rivers connected to climate change, and also like trying to guide us on how we will deploy a decision scaling framework. So I'm going to focus on the Tuolumne. One of the big innovations that we're pushing for the Tuolumne is this concept of weather generator and perturbation. So the weather generator sounds very geeky, but it's really a historical observed data. We're collecting, observed data from Livne, Prism, gauge data information, and we run it through these softwares, which is going to have different modules, like an annual, a seasonal, a daily, and an hourly modules to represent a long period of time series. So we can run, based on like 50 years of data, we can recreate 1,000 years of data with a representation of much drier droughts and much like larger events. So the many simulated time series of weather data. The nice thing with the weather generator is that we can perturb it in 2 different ways. We can perturb it using thermodynamic perturbation, meaning that the change in temperature, as I was mentioning in one of my first slides, is that we understand that by increasing the temperature, we are intensifying the atmospheric rivers. And so that's really this temperature change, this Clausius-Clapeyron process that I'm talking about is, how, we can perturb the intensity of the precipitation by increasing the temperature. The other perturbation that we can process and is not well understood by the climate change community is a dynamic perturbation. It's equal to the blob that we are talking in the Pacific Ocean. We stay in place. And these phenomena are not well understood. But with the weather generator, we could reproduce similar perturbations. So we're using this weather generator to really perturb the Tuolumne watershed system to understand what is the vulnerability of the system and resiliency. So here is a surface response plot. Same concept. The x-axis represents the change in mean annual precipitation, and the y-axis represents the change in temperature. Here represents a 97 event-like peak outflow. So the 97 event peak outflow was around 55.8 thousand CFS. Here the representation that the event we selected from our weather generator time series is around like 53,000 CFS. But on the snowpack aspect and how the watershed responded to this event is very similar in general. And again, each of these surface response represents, a change in the performance of the system. So at 2 degrees Celsius, with no change in annual precipitation, we show that the peak flow may increase by 45,000 CFS. So a peak of 98,000 CFS. We're doubling the flows. At 4 degrees Celsius, we are quadrupling almost the flow. We're increasing by 108,000 CFS. You can see like the surface response plots, the lines are very horizontal. What I tell you is that it's really driven by the increase in temperature. The increase in temperature is really the factor who's going to increase the snow melt, who's going to intensify the atmospheric rivers, and which is going to create a much larger event to handle. So now we can look at adaptation strategies. In fact, we look into 2 adaptation strategies. The first one, the plot on the left is the same plot that I just showed earlier. The plot on the top plots represent an increase in the channel capacity from 9,000 CFS to 25,000 CFS. And the plot on the right bottom represents a LunchMAR strategy, where we diverted, I believe, 1,000 CFS more than what is currently possible. So you can see that the black line, which is our current performance of our system, with an increase of 25,000 CFS of channel capacity, moved up. That means that we were able to buy ourselves some time to capture this flow. We still have a big problem of passing this flow when we are above 1 degree Celsius. We're still going to have a similar response to the system with an increase of 1 degree Celsius, but the channel capacity was able to create some sort of resiliency to the system. The LunchMAR was not as, doesn't provide as much relief to the system for the specific 97 events, but it can buy you between like around 0.5 to 1 degree Celsius. So now the idea is, how do you combine these strategies and how this combination of strategy can buy you, 1 degree Celsius, 2 degrees Celsius. And I think it's really like the key of the surface response is to really try to talk about how resilient we want to be. If you recall like the distribution of the general circulation models by the mid-century, the largest projection was showing a 4 degrees Celsius. And so is that what a decision maker want to reach, in the future, knowing that the probability that may happen is very small by 2050? And so it's really starting to have a discussion with stakeholders on like how resilient we want to be and what kind of a robust system we want to build moving forward. So takeaway here, that's, if you get out of this meeting, is that key climate change effects on hydrology are understood. Some of them are very well understood, that's the change in temperature, the increase in extreme precipitation, and sea level rise. I think there is enough literature there to understand. Something which is not well understood is the blob, for example. That's, some more science need to happen to truly understand what's going on and how to represent it in our system. There's two major climate change analysis approaches. There's a downscaling process and there is a decision scaling process. I think they are very compatible. Again, if you recall the Stillwater project, your fast response, you can overlay the surface response of your system with the general circulation model, the downscaling process, to have a better idea. The California Department is actively progressing in institutionalizing decision scaling in planning efforts. I think decision scaling is very useful for a planning exercise. Once you understand what is the level of resiliency that you want to achieve, then you may want to transition to a downscaling process where you narrow yourself to a very specific projection. And decision scaling can help decision makers by determining the level of resilience they want to meet and by selecting measures or adaptation strategies that can meet their needs. And finally, this decision scaling is these two watershed studies provide some guidance to our moving to action. That's an initiative that we have in the department to develop and provide better guidance to local entities and stakeholders in our decision making for water management in California. And it supports the water resilience portfolio. And I believe we have a last multiple choice question.
Okay, and here's the fourth question on how useful could decision scaling be in your decision making specific to climate change resiliency or FLMR project sizing? And as we were thinking about this question, we were recognizing that there's a difference between useful and being able to have the resource to readily apply it. But we wanted to think about the concepts that Romain presented and how useful that might be. And so people are responding with different levels. And Romain, while we're waiting for people, it would have been interesting to re-ask that same question again once you use an example to explain something to see if that helps people see, understand the concept better.
That's right. I think, based on the experience I have is, it takes 2 or 3 times to like really see the surface response and understand how much data mining you can get out of them. Because it's not only like the colorful of the data, but it's also you can dive into each of these perturbations and start to like, look into a specific drought in this time series and how the system performed during, this specific drought. So there is much more data behind it.
And it looks like people stopped, so I'm going to share the responses. Here we go. So I think your audience can validate the fact that this is a very important process to go through in thinking about resiliency and identifying vulnerability for systems. So I'll stop sharing. And we have time for some comments and questions. And Jenny, I realized that in my eagerness to get Romain to start talking about his presentation, we didn't get to really introduce you. So maybe you can do that and then identify some of the chat questions and comments, and really encouraging people to use the hand raise to share your thoughts in person as well.
No problem, Laurie. Thanks, Roman. That was a really great presentation. I'm Jenny Marr with the Department of Water Resources, one of Roman's colleagues, and working on our FloodMAR program. I've been monitoring the chat, so I've got a handful of questions, Roman, for you. And if anyone else wants to get in the queue to ask Roman a question, please feel free to turn on your mic. We'll catch that in the participants. Turn on your video or raise your hand, and we'll make sure to get everybody's questions addressed. So first question, Roman, is on the Sierra Nevada percent runoff graphic early in the presentation. Does the graph, do you have any sense of what the graph looks like today? So the first graph was 1981 to 2000. The graph below it was 2081 to 2100. So, you know, has that midway point changed in the last 20 years?
Yeah, I believe that there is already some studies which show that. I can send the paper to the group. We already explained that. In fact, you know, a lot of reservoir operators in the Sierra Nevada are already looking at that shift happening. In fact, they're also looking into like the annual variability aspect of it. So it's not only like a shift, which actually happening already, but it's also like, you know, the anterior variability that I didn't show, but that's, you can talk to Wes Monnier at Tuolumne Irrigation District, and it will point you out to the right data will show these changes. They are real. How far? I'm not sure. You know, it's hard because you need at least like 20 years of data to do this kind of a statistic, and just looking at one snapshot in a yearly base, it's very hard to look at it. But yeah, there is definitely studies who show that.
Yeah, and you and I have chatted about that graphic recently, and you know, the implications for adaptation strategies like FloodMAR and the different opportunities that shift in hydrograph represents. I've got another question from Phil. Are the GCMs considering climate effects that might switch, such as step changes in the jet stream or ocean circulation?
Yes, it does. They take that in consideration. Some of them are doing a very good job, unlike some others don't. But again, it's you know, it's a consensus aspect, and there is a lot of, you know, out of the 64 GCM, you know, there is some of them who are doing a very good job representing, like, you know, the change in temperatures based on the historical data, and some others who are doing very poorly. I think one of the big improvements that they have right now is on the representation of like the cloud covering and their energy balance. There is a lot of improvements that have been done, yet the range of future condition is still like the same as before. So as GCM are improving the representation of energy balance on the jet stream, and you know, historically, the projection variability or range is maintained. And so that's the difficulty behind it.
Great, thanks. Got a question from Chelsea. Is in the surface response responses that you've showed, is the 4-degree increase by 2050 in comparison to today's temperatures or an earlier date?
The 4 degrees Celsius is, yeah, so it's the way that we perturbing the data is we take the the current data, so 1,000 years or 100 years of historical data in temperature, and we shift everything up by 4 degrees Celsius. Again, it's not exact to what we are seeing with the GCM. The general circulation models are, you know, varying the change in temperature by location, by elevation, and other aspects. But I think it's a really good first step to understand how the system perform under 4 degrees Celsius. And then you can refine your analysis as you go move forward with the design or ER, EIS, where more, you know, you may want to select a GCM. So it's a the 4 degrees Celsius is not, it's just taking the historical data and move it up by 4 degrees Celsius.
Great, thanks. We've got a question from Andrea about Andrew's animation. And she was surprised that the center still hovers above that 0% change in precipitation, but kind of tracks upwards with temperature. And so do you want to speak to that a little bit?
Yeah. So what's happening is that on an annual base, what is really driving the precipitation is atmospheric rivers. And so what we are experiencing with like the thermodynamic aspect is that the increase in temperature have two effects. The first effect, it will allow it to carry more vapor transport throughout the Pacific Ocean and pour it in the Sierra Nevada, like atmospheric rivers are going to be more intensifying it themselves. But smaller events are going to get reduced in size because the increase in temperature is going to make them drier. And so that's why we don't really see a big change on an annual standpoint. But now if you were to get to zoom on a yearly intra-annual standpoint, you'll see like a big change in these events. So that's where like, the intensification, like larger runoff, like we see in the San Joaquin Valley, is going to be dramatic. But in the same time, we're going to have like, period of the year where we're going to have much less precipitation.
Great, thanks. Another question from Phil. For strategies, have you looked at significant and large changes in reservoir management, moving from storage to transfer without concern of current water right challenges? Yeah,
because there are a lot, so it's tricky because part of what I'm doing is R&D, and so we should be allowed to move forward and like change, make big changes in the system because that's really what we're trying to figure out. But in the same time, we are sensitive to local stakeholders, and it's important for us to work with them to move this like technology and this innovation. I cannot just try to put the system upside down and hopefully everybody is gonna be happy. I really need to work with like local entities to make them comfortable and build together a path forward for adaptation. I think presenting the graphics and showing the change, as we saw like the 97 events, increasing such a large magnitude, is talking to itself. And for a local entity to see this graphic, I think that really put the pressure on thinking outside the box, and that's where I think LunchMAR is great because that's outside the box, but we can size it as we're moving forward. So it's finding the middle ground between collaboration, pushing the innovation, and finding solutions together.
I've got a question from Graham. What steps is DWR taking to convey this very important information to lay audiences?
So we, in the climate change program, we have a group. We are, I believe we are 11 or 12 in our climate change program in the department, and we are matrixed inside the department. So we are not just one group, at the division of planning. We have one representative on like every sectors in the department. And so we have a working group who is specific to local entities and like also training and providing information. That's we do a lot of classes and training to educate people about climate change and future conditions. I'm not part of this working group. I can direct you to like the person. We can give you like more specifics about it. But we really trying to be not just inside the department. I think there's already a job inside the department to make sure that people who are working with me understand like the impact of climate change, but also the department. And we are trying to do our best with our small group working on climate change.
Great, thanks. We've got a question from Daniel. How is DWR using these approaches and results to engage the State Water Resources Control Board to inform analyses of future environmental flows and water availability or water available for FloodMAR and water rights?
That's a question for Kamiar. Kamiar, are you in the room? I saw your name. I don't know if you're paying attention.
Yeah, I'm here. Would you repeat the question just so I make sure I?
Sure, Kamiar. How is DWR using these approaches and results to engage the State Water Resources Control Board to inform analysis of future environmental flows and water available for FloodMAR and water rights?
Yeah, so as part of the implementation of the water resilience portfolio, Nancy Vogel convened a working group to look more closely at how water availability analysis that the State Water Board asks of applicants of water right permits compares to the work we have been doing on the Merced and the Tuolumne studies, including climate vulnerability assessment and the ways that it would affect stream flows, river flows. And we've made really good progress. This working group includes both Department of Water Resources and Water Board staff participants. So we're part of it was actually learning from each other what each of these are. And while we know in concept or in generality, it took some time to really get into the details of what goes into a water availability analysis, what goes into these watershed studies that DWR is doing, where they overlap and where they differ. And we're now writing up a proposal on how we could take information from a watershed study like Merced or Tuolumne, given that we've now overlaid climate vulnerability that's affected the flows that are there, and then taking those flows and porting it to the water availability analysis that one would do for a water board study. Because up to now, the water board asks folks to use their best historical data, at least 10 years, more if they have it, but that doesn't explicitly include what it would be in the future based on climate. So I think we're making some really good progress, and we'll have something to present in the next few months.
I think we have time for one more question. I don't see any hand raises or anyone in the queue, but I'll pause for a moment to see if anyone wants to jump in with one last question. Oh, I see one in the chat. How does the climate modeling address high variability in the historical record, which shows that recent California precipitation was higher than previous time periods with even century-long droughts?
Yeah, that's a good question. So, you know, the climate change and like the general situation, the way that they are working is really on their ability to represent historical data. And that's how, you know, we gauge. In fact, we had an effort in 2015, 2016. There was a climate change technical advisory group who work on figure out which general circulation models were performing the less well in California. And they went through the process of like removing the one who were not performing very well based on historical data. And they came up with like, you know, 10, 20 GCM, general circulation models, who were performing, you know, better than the rest of them. It doesn't mean that, you know, the one who were not selected are not a future path. And so that's what we are dealing with when we're working with climate change, is that we cannot guarantee that we know exactly what's going to happen. And that's why it's important to like really look at like the broad range of future conditions when we take our decisions, and have a consensus decision of how, you know, resilient we want to be based on the future conditions. The GCM are the best data available, and we rely on them on our decision. Now, related to the high variability of historical record, I'm not sure exactly where you're, you know, what you which show that the response coming from the precipitation was higher than previous time periods. I'm not sure if we can say for sure that recent records show like a higher precipitation. It depends, again, the period of time that you're selecting. If I take a 2-year or 3-year period and like compare it to like a 50-year period, it's not going to be comparing like oranges with oranges, and so you need to be very be careful when you're comparing this data to compare like apple with apple and not mixing up the data.
Yeah, great. Thanks, Roman. There's another question from Graham in the chat about mega drought research. So maybe we can touch base about that offline and put a response in the meeting, the LunchMAR meeting notes.
Yeah, I want to just mention something from Graham. I think there is some good data we came out from the Delta Adapt, from the Delta Stewardship Council. They just released their Delta Adapt report. We show some drought results, and I would recommend to take a look at that as well.
Great. Well, I'll say thank you again. Great presentation. Thanks to everybody who was able to join us. I'll put a final plug in for the LunchMAR Network workshop on Friday. We do have a link in the chat if you're interested in registering. And as always, if you're interested in presenting at a future LunchMAR, shoot me an email. I'll put my email in the chat as well, or just respond to the meeting notice. Thanks again, Roman, and have a great March, everybody.
Jenny, do we know who's speaking next month?
We have someone on the schedule. I don't like to advertise it because we get a lot of last minute cancellations and scramble to find someone else. So we have 2 options for March or for April. And I need to confirm with one of them in the next week or 2.
Thanks.
All right, well, thanks everyone. Just put a last poll just to see if you thought this was helpful to the work that you do. So I'm just putting that up as you're exiting. Thanks everyone for joining us today.
Thank you.
Thanks, Roman. Take care.
Thank you.
Thanks a lot.
Nice presentation, Roman. Thank you.